Hello and welcome to chapter 2. This is relatively a short chapter. We're going to be introducing the concepts of voltage and current, um, but you need to pay a close attention to what we're covering here because I'm not covering everything in the chapter. I'm leaving some things for you to read, and some other ones we're just not covering because it's not part of um, our focus on the course. So please pay attention to what we're going to be covering. We're going to start by looking at the basic concept of what current is or where the concept of current comes from. You may have already done this or hear this before, and maybe from your physics course or chemistry course before. But our intention is not to look at current from the physics point of view. We're going to be looking at current from a much greater point of view, as you'll see later, not from the electron point of view. Because in its essence, what current is the flow of electrons, okay? That's the basic physics definition of current, if you will. Is based on the flow of electrons. Well, to understand a little bit of that, we need to go down to the atom level and remembering what an atom is. And then if you remember from your physics courses or your chemistry courses in high school or in college, an atom is basically a form of two parts, a proton and an electron. And the proton is the positive component of the atom, and the electron is the negative component of the atom. As you can see that here from the hydrogen atom, which has one proton and one electron. The proton and some elements also have a nucleus. Okay, the nucleus doesn't have a charge, if you will. It's neutral. They don't contribute anything in terms of what current is. So in this picture, you can see the center of the hydrogen atom has a proton, and it has an outer band, and an outer band includes one electron. Okay, and what keeps this together is the forces that the two charges have. One is a positive charge, one is a negative charge. And so there's a force of attraction between those two that keeps those together. So in this example of a hydrogen atom on the left, the electron is pretty tight, close to the proton, and it's just flowing around that area. So so that's basically what you have in an atom, right? Now, depending on what type of element it is, the number of electrons that you'll have in each of those shells is determined by this number, 2n squared, where n is the shell number. So each of the shells is broken down into subshells where the number of electrons can be 2, 6, 10, 14, depending on what number of electrons there is for that particular element. So for our interests in electronics, we look at certain elements like copper, for example, which is the most commonly used conductor in electronics. And if you look at copper, copper includes 4 shells. Okay, as you can see here, it has 29 protons and 29 neutrons. And however, the last electron that it has is located at the outer shell, and as you can see here, it's by itself, right? If you look at this structure of copper, if you look at the inner shells, they're all pretty tight, right? They all have a number that is related to this 2n squared number, right? And as you can see, in the first shell, there's 2, and the second shell, there's 3, 5, 8, right, like the number implies, the 2n squared, and so forth. And so, but on the fourth shell, there's just one electron by itself. What that means is that this electron, and by the way, the further the shells are, or the electrons are located from the center, from the nucleus, the more loose they can be, okay? And in other words, the closer they are to the center, the tighter they are, right? The force of attraction is closer, is larger, if you will. And so the force of attraction for this last shell is going to be really weak, or at least weaker than the other shells. And what that means is that in the copper case, this electron here can be easily be set free, if you will, if we put another charge closer to this outer shell. If we put a positive charge closer to this electron, then that electron is going to be forced to go to the closer positive charge that it sees. So it's more freely to move than the other ones in the inner shells. Okay, and that's what causes copper to be a good conductor, because these electrons are going to freely move from one point to another. Okay, so there's a force, like we said, there's a force of attraction. If you look at this this picture, there's a force of attraction between the positive charges and the negative charges in this case, right? And obviously there will be a force of repulsion if we're the same. Like if you look at a magnet, right? If you put a magnet together, the north and the south attract each other. But if you put two north or two south next to each other, they repel each other, right? That's the force of attraction or the force of repulsion. Well, similarly, in the case of charges, right? If you look at charges, then there's a force of attraction and a force of repulsion between charges, whether the charges are positive or negative. And this force of attraction or repulsion is given by this equation. This is called Coulomb's law. Okay, and in Coulomb's law, F stands for the force. It's important that we pay attention to the units being used also. Okay, you remember from chapter 1 how important it is to keep track of the units, right, and making sure that we're using the correct units. So in this equation, F is and also it's important that you keep track of some of the letters that are used for this different parameters. In some cases, whether you use a capital letter or lowercase letter may not matter, but in most cases that we're going to be looking at here, the uppercase and the lowercase letters matter a lot. So that's also something to keep, really a close look on. So in this equation again, we're looking at the force of attraction or repulsion between two charges. F being the force in newtons is a unit of force. Q1 and Q2 represent the charges, right? So Q1 represents charge 1, Q2 represents charge 2. Q stands for the letter representing charge. R, on the other hand, is the distance between the charges. Okay, so in this case, the force is proportional to the product of the two charges and inversely proportional to the distance between the two charges. So R represents the distance between the two charges. And in this case, K is a constant. It's always a constant. It's always going to be given by this number. Okay, 9 times 10 to the 9 newtons per meter over Coulomb squares. And we'll explain this a little bit more in a little bit, what that really means. But just for now, just remember that this constant is always given by this number, okay? And by the way, in the future, as we go into future chapters, we're not going to be looking at electronics at this level. We're not going to be looking at charges per se, how individual charges at a tractor or repulsed among each other or whatever. We're going to be looking at this in a little more higher extent, but it's important that you understand where these major concepts are going to be coming from, and this is one of them. Okay, so again, this represents the force of attraction or the force of repulsion between two charges. Okay, so whether the charges are positive or negative, then you will have either a force of attraction or a force of repulsion. But remember, on the other hand, before I move on, that what's going to make current work is that we have this type of elements, okay, like copper. Copper has this loose electron in the outer shell, not loose completely from its own structure, but it can be more freely moved to another atom, for example, because it's further away from the center. The movement of these electrons, okay, the fact that these electrons can be moved easier is what's going to make current work, because current, as we'll see, is the movement of electrons. All right, so looking at this expression, okay, we can see that, and we're going to, by the way, we're going to be looking at some examples later in the next video. I'm going to be working on some of these examples so you can understand how these operate. But if you look at this equation again, okay, the equation represents, for example, if you have two charges separated by a distance r, how much of that force represents when the two charges have a particular kind of charge associated with them. Okay. Now, so let's just keep that for now, and we'll revisit it again when we look at some examples later. Now we're going to look at the concept of voltage. Okay, in the case of voltage, and by the way, when we look at this equation, okay, keep in mind that the charges themselves are represented by a letter Q. This is one of those cases where Q uppercase or Q lowercase can be used to represent charges. Okay, so you may find other books where they use lowercase q, and that will be okay. However, F capital cannot be used for other than force in this case. Okay, we use lowercase f means something else. So in this case, Q and Q1 and Q2 is given in units of what? The units of charge, and the units of charge are coulombs. Okay, coulombs. Capital C is used to represent coulombs. Okay, and the units of charge, like I said, is coulombs, and 1 coulomb is really a representation of a large number of electrons. And that number is given later here. And I just want to make a reference, because 1 coulomb of charge really represents the amount of a large amount of electrons associated with it. In this case, 1 coulomb represents 6.242 times 10 to the 18 electrons. Excuse me. So 1 single coulomb, okay, and then remember, we're using capital C to represent the units of coulomb. And 1 single coulomb includes 6.242 times 10 to the 18 electrons. Okay. Now, looking back now at the concept of voltage, when you look at voltage, there are several definitions associated with voltage. One of them is that voltage is the pressure needed from a power source to push electrons through a conductor. Another definition of voltage says that electrical force is an electrical force that drives current or electrons between 2 points that are connected together. Okay, it's really the amount of energy that is needed to move a charge from one point to another point. And you can see that in this example, in this figure on the left. If we're moving a charge, in this case 1 electron, from point A to point B, then that amount of energy that takes is what is called voltage. We call that voltage. Okay, and so every source of voltage is established by simply creating a separation of positive and negative charges. Okay, so you can see here in this example, right, that if you have two charges, in this case you have a positive charge or a negatively charged segment and a positive charged segment here, separated by a distance r, right? And if we move this charge from point A to point B, in this case, right, if it's moving from point A to point B, and if it takes 1 joule of energy to move it, and if the charge is that of 1 coulomb of charge, then we say that it's going to take 1 volt to move it. Okay? So really, voltage is associated with the movement or the potential of moving electrons from one point to another. Okay? That's why another name for voltage is also given as potential difference. So sometimes you'll hear the terms potential difference or voltage when you associate that to the concept of voltage. They both mean the same thing. But just remember that voltage means the total energy required to move one charge from point A to point B. And in fact, if you read this, it says if a total of 1 joule, again, in this case, joule is the unit of energy, right? And capital J is used to represent joules, okay? And says if a total 1 joule of energy is used to move the negative charge of 1 coulomb, there's a difference of 1 volt between the 2 points, okay? So 1 joule of energy needed to move 1 coulomb is what represents 1 single volt, okay? So the definition in equation form, we can define voltage, V, capital V. Normally, by the way, in a lot of these parameters that we use, we're going to use capital for voltage when we refer to DC voltage, and we're going to be using lowercase v when we use, or it refers to time-dependent voltage. We now, in our case, for this first course, all the voltages that we're going to see are going to be time-independent. They're constants. When you move into AC analysis, you're going to be looking at time-dependent voltage, and then in that case, you're going to see lowercase letters associated with time-dependent voltage. So for the DC case, we're going to be using V, capital V, to represent voltage. And notice here an important thing to understand, right? By the way, let me first define this equation, what this equation is saying. It's saying that the energy required to move a unit of charge is what the voltage is. Okay, voltage is the energy required to move a charge from point A to point B. So in this expression, if you look at capital Q, Q represents charge. Okay, and coulombs are the units associated with charge, right? We use capital C for the units of charge, okay? So it's important here that you really understand how we're using all these terms and all these letters to represent what they represent, because it can get really confusing because we're going to be introducing a lot of these new terms and a lot of these new parameters. So again, in this expression, just for Q, Q means charge. Q represents charge. Charge means a group of electrons, okay? Whatever that number is. It's just a large group of electrons. That's what we call charge. The units of charge are coulombs, the units. And we use capital C to represent the units of charge, all right? So we use capital C to represent the units of charge, then we use Q to represent charge itself, okay? In this equation again, capital W represents energy, okay? Capital W represents energy. The units of energy are joules, and the letter used to represent the units is capital J, okay? finishing up with the equation, capital V means voltage, okay, or voltage or volts or electrical potential, same thing. Electrical potential, potential difference, volts, voltage, okay. Voltage is represented by the capital letter V, and the units of voltage are volts. And we also use, in this case, the same letter to represent the units of voltage, which is volts. Okay. You can think of if this confuses you a little bit, you have used this before. If you took physics, you use this all the time, right? If you look, for example, at temperature, right? In physics, we use capital T to represent temperature, but we know what capital T stands for temperature, right? The units of temperature could be Fahrenheit, right? And so we use capital F to represent Fahrenheit. Same with distance, right? We normally use lowercase d to represent the parameter of distance, right? So little d means distance, and the unit of distance can be feet, right? Or miles. But if they're feet, we use ft to represent the units of distance, or mi to represent the units of distance in miles. So you understand the difference here, right? Yeah, again, look at d for distance, feet, and ft, right? Little d is the actual parameter that represents distance. Feet, which are the units of distance, are ft. Okay? So it's the same idea here, right? In this case, if you look at coulombs, Q represents the unit of the parameter of charge. The units of charge are coulombs, and they're represented by capital letter C. Okay? So it's important that you keep track of that as we move along. Okay? And of course, if you know the voltage is energy divided by the charge, then you can always solve for one of the other three parameters, right? In this case, energy will be the product of charge and volts, and so forth. So if you look at this example, it says, find the voltage between 2 points if 60 joules of energy are required to move a charge of 20 coulombs between the 2 points. So there's a point A and B, okay? And it says that in order to move that, there's a charge between 2 points A and B. In order to move that charge, it requires 60 joules of energy to move it, okay? And the charge is a charge of 20 coulombs. So moving that charge of 20 coulombs between point A and point B requires 60 joules of energy. In terms of voltage, then we say that the voltage between those 2 points is going to be given by the energy required to move that charge, which in this case is 60 joules, divided by the total charge, which is 20 coulombs. So in this case, the voltage between the 2 points is 3 volts. Now notice here another important thing is that if the units of energy and the units of charge and the units of energy is joules and the units of charge is coulombs, then automatically, because of the equation that we have here, the units of voltage are going to be volts. So this reads 3 volts. You understand? Just like this reads 60 joules and this reads 20 coulombs, this reads 3 volts. Okay? Not 3V, it reads 3 volts. Okay? Another example, it says find the energy needed in moving a charge of 50 microcoulombs. Remember this from chapter 1, micro means 10 to the minus 6. So the charge is 50 microcoulomb charge that is being moved between 2 points. If the voltage between the 2 points is 6 volts. Okay. So in this example, we're given the voltage. The voltage is 6 volts. We're given the charge is 50 microcoulombs. So we need to find the energy. So we can solve, if we solve for the energy, W in this case, the energy is going to be the product of the charge and the voltage. So, well, the charge is 50 microcoulombs and the voltage is 6 volts. So what we have is 300 times 10 to the minus 6 joules, or 300 microjoules. Notice that if we leave the answer like this, it's not the proper answer, although the number is correct. It's not the proper way of writing the answer. The proper answer is like this, okay? Because we have to use this prefixes associated with this powers of 10. Right? Remember that. This will be the proper answer, the correct answer. Even though this number is correct, the real proper answer is 300 microjoules, like that. Okay? All right. So in order to have another, by the way, we said also that we can say that voltage can also be described as potential difference between 2 points. Is another way of describing voltage. If you think of, for example, if you think of you being located, give me one. See if I can do this. All right. If you think of you being located at the top of a hill, right, and somebody else located at another hill lower than you are, right? There's a difference, obviously, between the 2 points, right? One is at a higher point, and your friend may be at a lower point than another hill. The difference between those 2 points is what is usually, there's a difference between those two, right? In the case of voltage, you can use the same analogy to say there's a potential difference between those 2 points. It's almost like saying, if you're a certain number of feet above ground or sea level, right? If sea level is your reference, then anything else will be above it or below it, right? It's the same thing with voltage or potential difference, okay? We'll see this a little more later when we get into Ohm's law and some of the other topics related to current and voltage. But just remember that we can also start looking at voltage as being a potential difference. Because remember, we did define voltage. One of the definitions we have is like voltage is the pressure needed to move charges from one point to another. Well, in order to have pressure, if you remember from your physics class, there has to be a difference between 2 points, right? In the case of voltage, there has to be a difference in between the 2 points for that electron flow to take place. Okay. All right. So another way of defining energy is also using what is called the electron volt. Again, we're not going to be using much of electron volts, but it's one of those terms that will be used in the book, and so it's important that you at least understand what that means. So if you look at electron volt is the level of energy required to move an electron to a potential difference of 1 volt. So electron volt is also a unit of energy. Okay, so if the level of energy that is required through a potential difference of 1 volt, and if you apply the basic equation for energy, which is here, then the energy will be in joules required will be this expression here, 1.602 times 10 to the minus 19. So it's just another way of representing energy. So in other words, 1 electron volt is equivalent to this number of joules. Okay, that's all there is to it. Or 1 joule is the equivalent of this number of electron volts. So take electron volt as another way of using units for energy. Okay. So that brings us to the concept of current. Well, since we already explained that when we apply a voltage, that voltage creates a pressure that makes the electrons move. So you can think of current as a reaction to applying a voltage, right? If you look at this figure for a moment, let me just go ahead 1 second. Right here, right? Normally, we have something like a battery which provides that voltage that we need, right? In DC, batteries are one of the main sources of power for providing that voltage. So the voltage is what's providing that push, okay? And in the case of a battery, yes, we always have a positive and a negative post, right? So going through if you connect a wire between point A and point B, in this case, the positive and the negative, with some element, in this case, you have a light bulb in between them, right? Then the moment there's a connection, right, there's got to be a closed path to create the final movement of electrons, because the electrons are going to leave the negative portion of the battery, the post. They're going to flow around the light bulb, and they're going to come back again back to the positive, right? And the flow continues, and it's going to continue until the battery runs out of juice, if you will, and it can no longer push those electrons, okay? So there's a chemical reaction happening inside this battery that's creating the push of those electrons, right? It's pushing the electrons out of the battery, back to the other side of the battery, out of one side, back to the other side. That continues until the battery dries out, correct? You're familiar with that. And so the movement of those electrons through through this element, in this case the light bulb, is what makes the light bulb glow, right? So electricity is the movement of electrons, in this case the movement of charge, okay, through some conductor during a certain period of time, okay. So that movement of electrons inside some conductor creates that what we call the electricity, okay. Now notice one thing, right, that physically excuse me, the electrons are going to flow from negative to positive, right, because the electrons are negatively charged and they're attracted to the positive, so they're going to be going towards the positive, right? You see that arrow here of electrons going from negative to positive. Well, that's called the electron flow current, okay? However, in most textbooks and in more conventional modern books that you're going to find, we use what is called conventional flow current. The conventional flow current is opposite to the electron flow current. And you'll see later why that's important, that we keep that convention. So for our purposes, we are not going to be using the conventional electron flow. Remember, electron flow is like, you think of it in terms of physics, right? Electrons are negatively charged, and so they're going to be moving towards the positive of this battery, right? So you can see this in the arrows, right? They're moving clockwise, right, in this example. Well, we're going to be using the opposite flow, and we call that conventional current flow. Conventional current flow is the opposite to electron current flow. Look at electron current flow, right? Electron current flow goes, in this case, goes clockwise. A conventional current flow will go counterclockwise in this case, opposite to the flow of electrons. So it may be a little unconventional or confusing at this point, but you just follow that rule. The conventional current flow, the type of flow we're going to use, is opposite to the flow of electrons. Okay, So make sure you understand this figure, because remember again, now we're looking at the relationship between current and voltage, right? Voltage is what's pushing those electrons, is what's causing those electrons to go out of one terminal back to the other terminal. It keeps that flow. Voltage is what's keeping that flow going on. Electricity is the fact that those charges are flowing. Okay? That's what causes electricity. And we use conventional current flow as the direction of the electron current flow, or the opposite of the electron current flow. Notice one thing, that whether we talked about conventional current flow or electron current flow, it doesn't change the actual amount of current. It's just it just changes the direction of the current. When we look at voltage, and you'll see that later, it's important that we look at not just the amount of voltage, but also the polarity of that voltage, and you'll see that later. The polarity will tell you what the reference of that voltage is. It's like saying, when you look at height, for example, if you look at something that is above sea level or below sea level, it gives you that reference, right? So the polarity is going to give you the reference. You'll see later that when we look at voltage, that polarity and that reference is important. So voltage and polarity go together, okay? Because it's important to know not just the amount of voltage, but also what the polarity is. Well, in the case of current, there's a similar situation, because we also need to know not just the amount of current, but also the direction of that current. Okay, so remember, this will make more sense later, but remember for one thing now, that voltage and polarity go together, and current and direction go together. Okay, all right. So the actual definition of current can also be given in terms of how much charge flows during a certain amount of time. One definition that we can have in terms of what current is by defining it in terms of its units. The units of current are amps or amperes. Normally we just use amps to talk about current, and we use capital A to represent those units. So in this case, if you have 1 coulomb, if 1 coulomb of charge, or 6.242 times 10 to the 18 electrons, and that's now you see why we use coulombs instead of using these large numbers, right? Because electrons are really so small by themselves. So we said if 1 coulomb of charge passed through some plane, like in this figure, in 1 second, then the flow of charge, or the current, is equal to 1 amp, or 1 ampere. And so that gives us the definition for the equation of for current. And this is the equation for current. So current is given as the amount of charge that flows during a given amount of time. Okay? The amount of charge flowing during a given amount of time. Okay? In this case, capital I represents amperes, or just amps. Okay? I is the letter used to represent current, the parameter of current. Amperes or amps are the units of current, and we use capital A to represent, not lowercase a. It's important that we understand that. Uppercase A to represent amps. Q is the charges we know in units of coulombs, and we use capital C to represent coulombs. T, lowercase t, is also important that we use lowercase t, because uppercase T means something else later. Lowercase t represents time, the units of time. In this case, this should actually say seconds, not time, because we're looking at, make sure you make that correction. This little t represents the parameter of time, but in this equation, the units of time that we're going to use are seconds, and we use lowercase s to represent seconds. So make sure you make that correction in your book if your book doesn't have it corrected, because this should say seconds. All right, the units of time we're going to use. All right, and so if you know I as the current, then in this equation you can solve for the charge if you want, or you can solve for the time if you want in seconds. Okay, it's important you understand that in this equation, in order for me or for you to obtain units of amps, the units of charge has to be coulombs, and the units of time has to be seconds. Okay, seconds. All right. So, for example, it says here that the charge flowing through the imaginary surface in that figure 210, and the figure 210 is this one here. We cut in that figure, and so there's, it's like you being here, the observer, and you're looking at that portion of the plane, and you're seeing how many electrons are going through during a certain amount of time, right? That's what this example is saying. The charge flowing through that imaginary surface is 0.16 coulombs. And so you see 0.16 coulombs every 64 milliseconds. So we want to know if that's the amount of charge flowing every 64 milliseconds, we want to know how much current is flowing. Okay? So again, if you look at the equation for current, right, is the amount of charge that flows during a certain amount of time. In this case, we have 0.16 coulombs flowing every 64 microseconds, right? So again, if you put this in terms of powers of 10, you can see how the 10 to the minus 3 will basically cancel in this case, and we have an answer of 2.5 amps. Okay. Again, the current in this case that flows is 2.5 amps. Okay? Not 2.5A. Okay, you will read this as 2.5 amps. Another example, it says if we have 4 times 10 to the 16 electrons that are passing through that same surface, and you know that the current is given as 5 milliamps, how long will it take for those electrons to pass if the actual current that you measure is 5 milliamps? Well, if you look at the equation here, then we're given the amount of charge, right? It's 4 times 10 to the 16 electrons. We're given the current, right, which is 5 milliamps. So what we need to solve for is time. What we're looking for is time. Okay. Now remember, since we have to be consistent in how we use the units, because this current is given in terms of amps or milliamps. So in this equation, remember, for me to obtain amps, the units of charge has to be in coulombs, and the units of time have to be in seconds. So in this example, I'm given the charge in terms of electrons. So for me to use the equation, I'm going to have to put this number in terms of coulombs, right? So I'm going to have to put this 4 times 10 to the 16 represented in terms of coulombs. And that's very easy, because if you remember, 1 coulomb is a constant. This is always given. 1 coulomb is equal to 6.242 times 10 to the 18 electrons. So that means that 4 times 10 to the 16 electrons, right, if we use this expression, is equivalent to 6.41 microcoulombs, right? So the important point here again is that in order for me to use that equation for current that I give you previously, I had to put this charge in terms of coulombs for me to use it. Now that in terms of coulombs, I can just directly apply it to the equation, right? Because I have 6.41 microcoulombs divided by 5 milliamps, right? Which is the current that is given, and that automatically gives me the answer in seconds. That's 1.28 seconds. Okay, so make sure you practice that. Okay, practice using the units, practice using these equations, And again, in a later video, we're going to be working some problems together so you have a little more practice, but it's important that you start understanding. Okay? So in summary, the applied voltage or potential difference in an electrical or electronic system is that pressure that sets the system in motion, and the current is the reaction to that pressure. Okay? If you think, there's an analogy used here, and I'm going to use it now, but it's also going to make a lot more sense when we look into chapter 4. Okay, but you can think of when you, for instance, if you hook up a garden to a hose, right? And of course, one end of the hose is hooked up to the faucet. And the other side of the hose will be, when you let the water out, right? Well, if the side hooked up to the faucet, it's if that faucet is off, obviously there's not going to be any flow of water, right? Obviously, as you start opening that water faucet, the valve, more water is going to flow, right? And you're going to see more water on the other end of the hose coming out. Okay, think of that pressure as the voltage, right? The more you open up that valve, the more pressure you have and the more water flows, correct? Think of the water droplets as the electrons or the current, right? The tighter or the more you close that water faucet, the less current is going to flow, the less water is going to flow. The more you open up that water faucet, the more voltage, the more pressure you're applying, the more water, the more current is going to flow. Okay, so that's kind of the idea behind the concept of voltage as the pressure, and current as that movement of electrons caused by the pressure. Remember, it's important that we remember what we talked about conventional current flow. Remember we said that in this book and in many other books, and I think in the rest of your courses in electronics, we're going to follow what is called conventional current flow. Don't be confused if you look at some other books and they use electron current flow. Okay, current is current. Okay, the current is not going to change. The amount of current is not going to change. It's the direction we choose as a reference that's going to change. So in our convention, we're going to be following conventional current flow, which is the opposite of electron current flow. Okay, so keep that in mind. Okay, so now we're going to move to voltage sources. On the left, you see the symbol we use for voltage sources, or just for a battery, DC voltage source, right? There are a few different ways of representing this. The bars, you can have just 2 bars, you have 4 bars, or normally it's 2 bars that you see like in this. The larger line represents the positive side of the battery, and the shorter bar represents the negative side of the battery. Okay, so if we follow that convention, we automatically will know that this is the positive charge and this is the negative charge without even knowing or without even labeling that positive or negative. By convention, the top one will be positive, the bottom one will be negative, the shorter end. Also, some books use capital E to represent voltage. I normally use capital V to represent voltage. In some books, the idea is that they use capital E to really show the voltage source, and they use V for other kind of voltages, but the voltage is the same. So don't be alarmed or confused if you see capital E or capital V to represent the voltage. In this case, what you're looking at here is the symbol for a 12-volt battery. Okay, 12-volt battery. All right. All right. So there's also another way, not just batteries, but there's also some other sources of DC voltage. It could be generators, a DC generator. In our case, for our practical purposes, when we look and start studying circuits, it won't make a difference for us whether it's a battery or a generator. It'll just be a voltage source. Okay, for our purposes, that's all we're looking at here, just a voltage source. And what you normally see again in all kinds of batteries, so you have a positive, you have a negative, like in this case, right? And normally what you'll see is two things associated with a battery, right? Well, depending on what kind of battery you have, it could be a DC, AA, AAA, whatever, some other types, right? But you see the voltage associated with that battery, but you also see other numbers like this one, right? You had said this number says 26 AH, 18 AH, and you'll see later what that means. Very shortly, we're going to see what that means, but that's another important way of characterizing what a battery will do, right? Not just the voltage itself, but also something that represents how much current you're going to get out of that battery and for how long. Okay. I'm going to leave you to read these details about the different kind of batteries and what they represent, right? Again, for our purposes in this class, we are not gonna be focused on what kind of battery we have, what kind of source we have, whether it's lithium or lead acid or whatever. That's not gonna be our focus, because all we're gonna be seeing or using is a battery, whatever that battery is, or whatever that source of DC voltage is. But it's important that you read this. So I'm going to leave you to read this on your own, and just so you're familiar with different type of technologies that are behind batteries. But for our purposes, again, a battery is a battery. Okay, that's even if it's a solar cell, or a generator. For our purposes, we're just going to be looking at that as the source of voltage. So the section on batteries, if you read it, is really optional if you want to read it. I encourage you for you to read it because it'll give you more knowledge of what's going on, but it's not required that you read it. Okay. Later in the lab, we're going to be looking at more detail at power supplies. And again, power supply is just a source of voltage, right? Think of it as a battery. Okay. In the lab, this is the type of equipment we're going to be using as our sources for energizing the circuits. And so when we're looking in the lab, we're going to be looking at this in detail, practically in detail. All right. You can skip this section on fuel cells. Again, if you want to read it, it's really great if you do. It's really good knowledge to have, but you can skip it for our purposes if you want. The other concept we need to understand is what we mean by ampere hour rating. Okay, and it's shorted out as AH, capital AH. And you notice, right? Remember I told you before when you buy a battery, a lot of times you don't look at that other number here. We normally just look at the voltage, right? And you notice here that all of these batteries provide the same amount of voltage, right? 1.2 volts, all of them, whether it's AAA, AA, C, or D. The major difference between these different shapes and sizes is that each one provides or may provide different amount of current, right? Like you can see here, right? This one can provide up to 500 milliamps. This one can provide up to 140 milliamps, right? And the other number that is important here that we mentioned before is this milli AH, okay? Right? See how this have different numbers, 700 milli AH? Well, that's what we're going to explain right now. And the AH has to do really with how long a battery can provide the amount of the amount of current it says it's providing. For how long are you going to get that current? And that's important, right? Because not only the voltage that you need, but for how long that voltage is going to sustain that current. Okay? And that's what this parameter has to do with. The ampere hour rating is the most important piece of data after the voltage itself. So in the definition, again, the idea is that the ampere hour, or the AH rating, gives you an indication of how long a battery of certain voltage will be able to supply a particular current, for how long, okay? And is defined like this. It has to do with the life of the battery in hours. The life of the battery in hours is defined as the ampere hour rating divided by the amount of current it draws, okay? So for example, a battery with an ampere hour rating of 100 will theoretically give you a current of 1 amp for 100 hours. Okay, 1 amp for 100 hours, or 10 amps for 10 hours, or 100 amps for 1 hour. Okay, so the greater the current, the shorter the amount of time, right? And so that's what this relates to. Okay, for example, it says you have a 9-volt battery, and you read in the specifications for that battery, it says that it has an ampere hour rating of 520 milliamp hours. So it says, how long will this 9-volt battery provide a current of 20 milliamps? Well, if it has a ampere hour rating of 520, right, this is the ampere hour rating, and is giving you 20 milliamps. Given this equation, if we divide this one over the ampere drawn, then you get the life of the battery in hours. So if it's 520 milliamps hours divided over 20 milliamps, then it will be able to provide you 26 hours with a current of 20 milliamps, if that's the rating of this 9-volt battery. Okay, so for 26 consecutive hours, theoretically, that battery will provide you with 20 milliamps. That's what that number means. This is what that number is telling you here. Okay. Another example says, how long can a 1.5 volt flashlight battery provide a current of 250 milliamps to light the bulb if the ampere hour rating is 16 amp hours? Again, we're looking for how long, okay, how many hours. Well, in this case, this battery is rated as 16 amp hours, okay? And so, remember, the amp hour is an indication of how long the battery will give you a fixed amount of current. So it says that it's a 16 amp hour rated current, and it says for how long that battery can provide you with 250 milliamps. Well, if we use again the same equation, making sure again is important by the units, like I said before. When we use these expressions, we have to pay attention to what kind of units we're using. In this case, the amperes or the amps has to be in units of amps, not milliamps, not microamps, you know, whatever, in units of amps. And the amp hour ratings, of course, will be in hours, right? So if this is given as 250 milliamps, then we have to put this in terms of amps. So we have 250 times 10 to the minus 3 amps, and divide that 16 into that number will give us the total number of hours that this battery can provide you with 250 milliamps. So in this case, for this particular battery, the way it's rated is rated as 16 amp hours. It can give you 64 hours of current. So how much? This much current. Okay. All right. Section 2.7. We're not gonna really look at that in detail. For one reason in this case is because for our purpose of analysis, right, when we start looking into analysis, this is an introductory course. We're really assuming that we're dealing with ideal components. In other words, if you look at a battery, we're assuming that we're going to be looking at ideal batteries. If we say the battery we're going to use is 1.2 volts, then we're going to assume that that 1.2 volts is going to last us as 1.2 volts, and it's not going to change. Well, we know that practically that's not true, right? Because batteries have a life. Batteries work differently depending on many factors, depending on things like temperature, for example. Batteries can go down, quickly under different temperature conditions. We also know that batteries, even though they might be rated a certain amount of providing certain current, they're not going to provide the same amount of current throughout the life of the battery, as you can see in this figure, right? Ideally, we say, well, if the battery is rated at 25 milliamps, it's going to give you 25 milliamps until it dies. Well, that's not true, because with the life of the battery, as the battery ages, the amount of current it provides is gonna change. Okay, because of the nature of the battery itself. So things change in a battery, right? They're not ideal, whether they're temperature related, whether it's related to the life of the battery. So this is what this section is about. But for our purposes, again, of our initial introduction to this type of circuits, we assume that the batteries are ideal, and that the amount of voltage that they provide is not going to change. It's not going to move. It's going to be constant. But practically, be aware that that's not the case, right? So that's what this is saying in this section. So read that section, but knowing that for our purposes, we know that we're going to be using ideal batteries, right, when we analyze circuits. All right. The last thing I want to talk about in this chapter is about conductors and insulators. Excuse me. And as the name implies, conductors are those materials that will allow the flow of electrons easily through them. Okay, when we apply a voltage through a conductor, a wire, copper wire is a good example, is a very good conductor, then what that means is that if it's a conductor, and especially if it's a good conductor, current is going to flow very easily. And that's why copper, for example, is a good conductor. It only has, if you remember, it only has one electron in the outer shell, and so that electron can be very easily be moved. Okay, and there are all kinds of conductors, like in this table indicates. Silver is even better than copper, but of course silver is a lot more expensive. In terms of conductivity, is better, but copper is really the most commonly used type of conductor. Okay, and so a conductor is just that. Is a material that allows current electrons to flow very easily. And on the other hand, you're familiar with the concept of an insulator. Well, an insulator is the opposite, right? Insulators allow very few movement of electrons, or very few electrons to flow. Okay, air is an example of an insulator, porcelain, oils, and so forth. Okay, so it's important that we understand in circuits, what a conductor does and what an insulator does, and they both do important work when we look at circuits. We're not going to be using or looking at semiconductors. Semiconductors are it's a mixture of the two, if you will, if you want to know that. It's a mixture of a good conductor and a good insulator. Okay. And you're going to be looking at semiconductors later in electronics, not even in AC, but maybe later in electronics. Then you're going to be looking at this type of materials that they're called semiconductors, because they can be good conductors during some times, and they can be good insulators during some times. And you'll see why important that is later when you look into electronics. But for our purposes, we're going to be just looking at conductors and insulators, okay? Mainly conductors, right? Understanding that conductors allow the flow of electrons very easily, the flow of current. Ammeters and voltmeters, this is something we're going to be looking very closely in the lab. But for now, just understand that an ammeter, like the name implies, is used to measure amps. So ammeters are used to measure current. Voltmeters are used to measure volts. So voltmeters are used to measure voltage, right? And we're going to be looking at this in detail in when we look at the lab section in the course. This is the type of multimeter we're going to be using, digital multimeters. We're going to be using also other kind of multimeters. This is an analog multimeter. This is the old type analog meters. We are not going to be using analog meters in our course, in our lab. We are basically going to be focused on using digital multimeters among other devices we're going to be using. But just keep in mind, again, we're not going to be using analog devices. This is an example, a picture of the display for an analog meter. That's not what we're going to be using. We're going to focus on digital multimeters. But just keep in mind that those digital multimeters is what's used to measure, among other things, voltage and current. All right, so this concludes this chapter. What I'm going to do is on the next video or the next lecture, we're going to be working some problems so you understand a little more how we applying the concepts that we're applying in this case.